This paper was going to be presented by my colleague, Professor Jesus Rodriguez, but as Pamber has said, he has had to leave at the last moment. So I'm going to try to do my best, okay, with his presentation. Hydrogels are biphasic materials formed by a polymeric network plus a large content of water. And due to this large content of water, hydrogels are mainly used in biomedicine and bioengineering applications because of the biocompatibility of these materials. The mechanical behavior of these materials is very complex. First of all, they are soft materials with a very low stiffness of the order of kilopascals. They have a nonlinear mechanical response and time-dependent properties due to two different phenomena: viscoelasticity, that is caused by the rearrangement of the polymeric network during the formation, and peroelasticity, that is caused by the migration of the water or the solvent inside the material. To extend application of these materials to other technological sectors, it is very important to know the fracture behavior of these materials. And the problem is that to obtain correct fracture properties of these materials is a challenge. Of course, our group is mainly experimental, and during the last time we have been working on the fracture characterization at the micro scale of these materials, and we have had to face several difficulties that nobody talks about. The first one, how to grip these materials. The second one, we have to work with low transducers in the range below 50 newtons, because the load at failure of these materials is, in the best case, of a few newtons. And most of the tests must be carried out in underwater, in immersion. And because this, together with the softness, it is very difficult to use physical or contact transducers to determine the elongation of the formation, and we have to apply the digital image correlation. But not every paint can be used to generate dot speckle pattern. Anyway, we have tried to do our best to get fracture properties of fracture behavior of these materials at the microscale, and we have applied several methodologies to obtain the fracture response. For example, the Rivlin and Thomas procedure that is normally used to determine the fracture behavior of rubbers, and also fracture mechanics approaches, nonlinear fracture mechanics and viscoelastic fracture mechanics that I have talked in my first presentation. Anyway, the fracture characterization is very complex. That's what I want to say. But in these materials, normally, to determine the mechanical response, many researchers use indentation tests at different scales because it's much easier. And the contact models, the one that is mostly used is the Hertz contact model that establishes a relationship between the depth penetration, the contact radius, and the applied load. Of course, in this model, we also have to have some taking into account geometrical terms and the elastic properties of the material of the indenter or the material of the sample. It is important to highlight two things about this model. It's only valid for fully elastic materials, and hydrogels are viscoelastic and peroelastic materials. And in case of indentation at the nano or micro scale, we have to take into account the adhesion energy between the material of the indenter and the material of the sample. And Johnson, Kendall, and Roberts modified the Hertz equations to introduce the adhesion energy, omega. So the reason is try to apply the indentation test in these viscoelastic materials using contact models from the continuum media. So the objectives is to study the adhesion phenomena in hydrogel by means of a sphere plane indentation process, to develop procedures to estimate the adhesion energy through contact models based on continuum mechanics, considering the viscoelastic behavior of the hydrogels, and now the relationship with the fracture, of course, to compare the adhesion energies with the fracture energies in a family of polyacrylamide alginate hydrogels, but obtained with with tests at the macro scale. Okay. Three materials were studied: polyacrylamide, PAM, and polyacrylamide with a 10 weight% of alginate, and polyacrylamide with 14 weight% of alginate, PAM 14 ALT. I'm not going to say anything about the manufacturing process, but if anyone is interested, I can give them later the details. The experimental procedure. Okay. Low relaxation non-indentation tests were carried out using a glass spherical indenter of a radius of 100 microns. And the test consisted in the application of a penetration depth constant of 1 micron and maintained constant afterwards, and the load was recorded. From these two experimental data, we have applied the JKR model, the Johnson, Kendall, and Johnson, Kendall, and Roberts model to obtain the relaxation function GT and the adhesion energy omega. And once again, I want to repeat that this model is fully elastic, but this material is viscoelastic. So we have created an analysis method that that is based on the application of the correspondence principle that in an easy way converts a viscoelastic problem into an elastic problem using the Laplace transform, the Laplace-Carson transform. Okay, we start with this experimental data, the penetration depth as a function of time, and the load evolution as a function of time in the time space t. Okay, then we applied the Laplace-Carson transform, and we obtained this experimental data, but in the transform space P. And in this transform space, the constitutive equations are fully elastic. So we can apply the JKR model for every every pair of data, penetration depth, and load. And we obtained the relaxation function and the adhesion energy function, but in the transform space P. Okay, we applied the inverse transform and we obtained a relaxation function and an adhesion energy function in the time space P. Okay, let's move to the results. In the graph on the left, we only have plotted the penetration depth imposed in the materials. And in the graph on the right, there is it is shown the load evolution for each material. I want you to focus on the scale of the load of several hundred of nanometers. Okay, so we have applied the Laplace-Carson transform and we obtained the penetration depth and the load in the transform space as a function of the transform space. And then for each pair of values, we apply the JKR model in the transforming space, and we obtained the Rayleigh section function in the transforming space for its material, and we applied the inverse transform, and we obtained the Rayleigh section functions as a function of time. Not even that, we have been able to obtain the energy adhesion for its material, and the energy adhesion resulting from the application of the JKR model are these dots with different colors for each material. And we have also plotted the J-integral crack growth initiation as a straight line. These values are obtained from fracture tests at the microscale. And we observe that there is a nice similarity between these two terms. To check the consistency of the results, apart from the non-indentation low realization test, we have also carried out torsional realization tests in these materials. And in the graph on the left, we show the shear modulus at equilibrium. And in the graph on the right, the instantaneous shear modulus of the different materials. Okay, we can observe that these values obtained from different experimental data are very similar. So, well, I think that the results are not so bad. Instead of conclusions, I want to launch some open questions because, of course, we're exploring, we are investigating on this. The first one is there a real relationship between the adhesion energy and the fracture energy? And if so, can the fracture properties of these materials be obtained from much easier tests like non-indentation test? And if so, is it applicable to all types of hydrogels? Anyway, we have used the JKR model, but is it appropriate? Can we use other contact models like Mauch's ductile contact model? Well, we have to make some research about this. And what about peroelasticity? We have not talked about peroelasticity. Well, we know that peroelasticity is not only time dependent, also size dependent. And at the test at the nano scale, the peroelastic behavior can be considered not relevant at all. And how relevant is the constant Poisson ratio hypothesis? Because we have